Let us consider a practical problem. If a plane wave passes through a rectangular slit, what will be the Fraunhofer pattern at the screen? This rectangular slit can be described as this one. In the plane of x0 and y0, the shape of the slit is rectangular. With the length in the x0 axis is d sub x, and the length along the y0 axis is dy. And now we want to find out the Fraunhofer field pattern of the slit. So consider in the far field region. We have learned that the Fraunhofer diffraction pattern can be obtained as the following equation. The Fraunhofer diffraction can be expressed as this equation, with the amplitude is in proportion to the Fourier transform of the initial amplitude, with the parameters switched to k over z times x and k over z times y. Besides, as I have said, here this term represents the curved waveform. And now we have to find out this function to help us to obtain the differential amplitude in the far field region. So to find out the Fourier transform of the initial amplitude, we have to express the initial amplitude u sub 0. According to the plot here, we can define the initial amplitude u0 in this way. Okay, so due to we have a rectangular slit, only in the rectangular slit we have the field with the amplitude is 1. In other position, the field will be 0. So this one is our initial amplitude. And now we have to find out the Fourier transform of this initial amplitude. So let's go back to the Fourier transform. Consider a rectangular function like this, and what will be its corresponding Fourier transform function. And we have learned that the Fourier transform function of this rectangular function will be the sinc function. Okay, so for u0 it is a rectangular function, and the Fourier transform will be a sinc function. And the sinc function is defined as sine over x. Sine x over x will be the sinc function. So let's find out the Fraunhofer diffraction of this problem. The initial amplitude here, U0 function, can be written as rectangular function of x0 over d sub s times rectangular function of y sub 0 over d sub y. Okay, so according to the Fourier transform of the rectangular function, we can write down the Fraunhofer diffraction of this initial amplitude to be u of x, y, z is like the following expression. To obtain this result, you have first know the Fourier transform of the initial amplitude. But if you don't know the Fourier transform of the initial amplitude, you have to take the initial amplitude into the Fraunhofer diffraction integral. Okay? So we first write down the Fraunhofer diffraction of a rectangular slit here, and in the following slide I will show you how to obtain the same result from the integral equation. As we know, the Fraunhofer diffraction is an approximation of the Fresnel diffraction. So for Fresnel diffraction in the far field region, the diffraction amplitude can be approximated as the following equation. And the integral, we can take the definition of the rectangular slit U0 into this integral. The above equation can be simplified as the following equation. Okay, due to the initial amplitude, amplitude can be expressed like this. We only have value at this condition, and the initial amplitude is 0 for the other conditions. So the integral can be simplified as the integral from minus d sub s over 2 to d sub s over 2, and minus dy over 2 to dy over 2. And then how to find the result of this integral. we take the integral with respect to x, for example. For x, we have to find out the result of this one. This equation integrates s sub 0 from minus dx over 2 to dx over 2. So it is a very simple integral for you. You can obtain the result to be this equation. And take these two values into this one. The integral will be as the following form. Okay, and clearly it will form a sine function, so the result will be z over jkx times 2j times sine kd sub s over 2z times x. And after some arrangement, it can be re-expressed as sine function divided by this value. So the integral with respect to x0 can be obtained as this one. Then the total integral can be written as this equation. Okay, so it is very easy for you to find out the Fraunhofer diffraction for a simple initial amplitude. You should learn how to obtain the final value by yourself. And from this result, as I have said, the Fraunhofer diffraction will be in proportion to the Fourier transform of the initial amplitude. And for this rectangular slit, the Fourier transform will be a single function. So you see, the differential field will perform as a single function shown here. In previous slide, you can also see the single function in x and in y directions. Okay, so from this single function, I would like to ask you a question, that is, where can we find out the first null of the diffraction field? Clearly, from this figure, you can see the first null means the first 0 point. The first 0 points will appear at these 2 points, right? So from the expression for the diffraction field, can you find out the first nulls? So from this expression, you can see that To obtain the zero diffraction field, the psi function should be 0. So, as psi, if we consider acceleration first, if psi of kd sub x over 2z times x, if this psi function is 0 and meanwhile x is not 0, we will obtain the null along the x direction. Similarly, if psi function is 0 and y is not 0, we will obtain the nulls along the y direction, right? So what will be the x value or the y value for these two conditions? And clearly, to have psi to be 0, the x value should satisfy that this expression should be positive or negative pi, which will correspond to the first nulls. Okay, and for y, they should satisfy that this term will also be positive pi or negative pi. So from these two conditions, we can find that the first nulls along the x direction will be x is positive or negative 2z pi over k times d sub s. Okay? And then we know that the k value can be replaced as 2 pi over lambda. So the null will appear as s is lambda z over d sub x. In the same way, the first nulls along the y direction will appear as y to be 2z pi over k d sub y, which can be also written as lambda z over d sub y. Okay, so from the derivation here, you can obtain the location of the first nulls along the x direction and the y direction. And another important parameter is that if we have somebody standing here, he look at the first nulls, what will be the angle with respect to the z-axis? The angle I plotted here is defined as diffraction angle. Okay, so as z is very large, which means that the screen here is far away from the slit. Then we know that the tangent c dot x, we define this value to be c dot x, will be the value of c dot x will be very small. So tangent c dot x can be approximated as c dot x. Okay, and this value will be very small compared to 1. So from the definition of the tangent c dot x, we know that it will be the ratio of this 1 to this 1. So we know that the tangent c dot x will be approximately to c dot x will to be lambda z over d, sorry, I should write it like this, lambda z over dx divided by z, which can be written as lambda over d sub x. Okay, so similarly, the c dot y can be approximated as lambda over dy. Okay, so this is the important property for the Fraunhofer diffraction.